Okay, I am Bo Berntsson from Chalmers University of Technology in Gothenburg, Sweden, and I'd like to welcome everybody to this special sectional lecture of the ICM. It's entitled Recent Progress in General Relativity, and it's a joint lecture with two speakers, Gustav Holzegel from the University of Münster and Peter Hintz from the ETH. Please. I'll leave the word to the speakers.
Thank you very much for the introduction. First of all, Peter and I would like to thank the organizers for the honor to speak here, and also the local organizers for organizing the live event, which is of course very nice to give this talk to a live audience. So this talk is going to be about general relativity. So let me start by reminding you what general relativity is about. So the object of study are four-dimensional Lorentzian manifolds, four manifolds equipped with a Lorentzian metric, a metric of signature minus plus plus plus, and this is a model for our space-time. So the simplest example is R4 with the flat metric, which is Minkowski space and familiar from special relativity. Now, because of the Lorentzian signature, a vector in the tangent space can have negative, zero, or positive Lorentzian length, and depending on that, we call these vectors time-like, null, or space-like. And the null vectors form a double cone separating the time-like vectors from the space-like ones. And you call one of the cones the future and the other the past. And if you can do that consistently over the manifold, it's a time-orientable Lorentzian manifold, and that's a space-time. Now, the notions of time-like, null, and space-like are inherited by curves. So you can talk about time-like, null, and space-like curves, and geodesics play a special role in the theory from the point of view of physics, namely the freely falling particles move along time-like geodesics, and null geodesics are the light rays. Okay, so we're not just interested in any Lorentzian space-time, but into those satisfying the Einstein field equations, which I've written here in one. So R mu nu is the Ricci tensor of G, R the scalar curvature, lambda the cosmological constant, and T mu nu the energy momentum tensor of the matter in space-time. So that's, you should think, is a second order nonlinear PDE for the Lorentzian metric G. And you should compare this with the equation that the Einstein equations replace, namely the equations of Newtonian gravity, which are also second order, but elliptic equations where you specify a mass density and then you solve for the gravitational potential phi, which then gives you the gravitational field and so on. However, the interesting thing about the Einstein equation is that even in the vacuum case when no matter is present, the Einstein equations are non-trivial. And in fact, in this talk, we'll reduce mostly, at least, to the Einstein vacuum equations, which I've written at the bottom. Okay. Right. So the reason the Einstein equations are non-trivial even in vacuum is rooted in the fact that they're essentially wave equations. And the geometric formulation of the associated Cauchy problem is through the fundamental theorem of general relativity proven by Choquet-Brouillard and Choquet-Brouillard-Garroch, which state that the Einstein equations have a well-posed initial value formulation. And what is this formulation? You start with a Riemannian free manifold sigma h and a symmetric tensor k, which satisfies certain constraint equations and possibly boundary conditions if a boundary is present. And then you can associate with that a unique maximum development, which solves the vacuum Einstein equations and is such that the slice sigma embeds as a slice with first fundamental form H and second fundamental form K. And what general relativity really is about is the study of this maximum development. You want to know its geometric and analytical properties. And there are two immediate challenges that you can appreciate. One is the equations are nonlinear, which makes answering questions about the maximum development difficult. And there's also the diffeomorphism invariance. So the Einstein equations don't make reference to any coordinates, but to do analysis, you need to work in coordinates. But then if you prove some singular behavior, you have to make sure that it's really geometric and not because of your bad choice of coordinates. In any case, the theorem that I quoted there allows us to ask two questions that we'll focus on in this talk. And this is the question of stability, where you're perturbing data for which you know the maximum development very well, typically exact solutions. And the second question is that of singularity formation. So we want to understand the boundary of this maximum development. Okay, so before I tell you something about exact solutions and their stability, let me introduce two ways of writing the Einstein vacuum equations as a well-posed system of partial differential equations. So these are not the only ways to write them, but these are two ways that have been used a lot in the past 10 or 20 years to make progress, and they also play a role later in the talk. So let me introduce them. The first is perhaps the most well-known, is the harmonic gauge, in which the Einstein vacuum equations become a system of quasi-linear wave equations for the metric components, G mu nu, and that's also the gauge in which you prove typically the theorem on the previous slide. And it had also been used successfully in global problems like stability of Minkowski space in the Lindblad-Rodniansky proof, and also nonlinear stability of the slowly rotating Kerr de Sitter black holes that we'll hear about later. One little drawback about this is that the nonlinearity in this gauge only satisfies the so-called weak null condition. And the second way to write the Einstein equation that I want to introduce is the so-called double null gauge, in where the idea is that you foliate space-time by ingoing and outgoing null hypersurfaces intersecting in space-like two surfaces, typically spheres, as shown in the picture. And then you write down a system for the geometry for relating the intrinsic and extrinsic geometries, and you obtain a system of transport equations for the connection coefficients along the cones, which is coupled to a hyperbolic system of equations for the curvature following from the Bianchi equation. So there again, you see the wave nature of the Einstein equations. And this system is very complicated, and it's now a mix. It's not only wave equations, but because gravitational radiation propagates along null hypersurface, you get access to the fine aspects of the space-time geometry, and in particular, the null condition that's so important for nonlinear wave equations is manifest in this gauge. And this gauge has been used in a variety of contexts: formation of black holes, impulsive gravitational waves, construction of naked singularities, things that we'll hear about later in the talk. So it's a very versatile gauge. Okay, and with this, I turn to some of the exact solutions to the Einstein equations, and let me start with the maximally symmetric ones. The first one, in the case lambda is equal to 0, cosmological constant vanishing is flat space, which I already mentioned. I don't want to say much about this, except that I've drawn a Penrose diagram of the space-time on the right. So relativists like to think for space-time in terms of conformal diagrams, from which you can read off the causal structure of the space-time in a pictorial way. And I just want to draw your attention to this set null infinity scri plus and past null infinity scri minus, which corresponds to the endpoint of future-directed, respectively past-directed null geodesics. The solution for lambda bigger than 0 is called de Sitter space and describes an expanding universe. So the feature there is that null infinity is now space-like, future null infinity and past null infinity. And the solution for lambda smaller than 0 is called anti-de Sitter space. And there you see the set scri null infinity is now time-like, which means that if you want to make the Einstein equations well posed, you have to impose boundary conditions at this conformal boundary if you want to construct anti-de Sitter type solutions. Okay, so these are the maximally symmetric solutions for the various cosmological constants, and for lambda bigger than 0 and lambda equals to 0, there are classical theorems regarding their stability. So for lambda equals 0, we have the theorem of Christodoulou and Kleinerman on the stability of Minkowski space, which states that if you start close to trivial data and you look at the maximum development, then it's geodesically complete and asymptotes to the Minkowski metric along any geodesic. And for lambda bigger than 0, we have stability of de Sitter. There you can use the so-called conformal field equations, which Friedrich did, where the problem essentially reduces to a Cauchy stability for a conformally rescaled metric. And there's still further developments on these classical theorems. You can couple with various meta models, you can improve regularity and so on. So let me not go into that. And let me focus on the what is perhaps the most interesting case from the point of view of stability, which is the case lambda is smaller than 0. So as I said, there the local problem is an initial boundary value problem. You have to impose boundary conditions at the conformal boundary. And this is actually open, so we still don't understand the stability or instability, and it's expected, as I put in this conjecture, that this will depend very much on the boundary condition that you impose. So if you impose dissipative boundary conditions, then energy can leave the spacetime, and you expect that the maximum development asymptotes back to ADS. But if you impose reflecting boundary conditions, then the expectation is that you have instability, that you form that even arbitrarily small initial data will form a trapped surface and eventually a black hole. So that's open, but fundamental progress was made for a toy problem, for a spherically symmetric toy problem, the Einstein-Vlasov system by Mosidis some years ago, and he proved that ADS is unstable for that model, and he in fact proved that trapped surfaces will eventually form. So I just want to say one sentence about the proof. So the proof is a completely physical space argument. So it consists in cooking up a very intricate initial arrangement of Vlasov beams, which get reflected at the boundary multiple times, many times. And he identifies an energy transfer mechanism that happens with every reflection, which allows to move energy from the lower beams into the top beam, and eventually the energy will concentrate so much that you form a trapped surface. So that's a physical space mechanism, but there's an intimate relation with weak turbulence. And yeah, so that's an interesting problem. And as I said, the conjecture is open. With this, I end the discussion about the maximally symmetric solutions and hand over to Peter for black holes.
Thank you very much, Gustav. And also from my side, thank you to the local and virtual and global organizers of this conference for the very kind invitation. So following these maximally symmetric solutions, the next solutions that were found have less symmetry. So in this case here, spherical symmetry in the spatial variables. So the Schwarzschild solution was found already in 1915. And at the very top, you see the formula for the metric in a certain coordinate system. The only thing that I want you to notice is that this metric depends via this function f of r on the cosmological constant, which is a parameter of the theory, and this additional constant m, which is the mass of the black hole, so which will be positive. And also here you can draw these Penrose diagrams to understand the causal structure of these spacetimes. And so what's drawn here is the Penrose diagram of the largest analytical spacetime that contains this coordinate patch up there. And so let us focus on the right diamond in that picture. And so you see that you again have, in view of the fact that this metric asymptotes to the Minkowski metric when R gets very large, you again have null infinity, future and past null infinities, chi plus, chi minus. But there are novel features of this spacetime here due to the presence of this, this mass term. The first feature is the presence of an event horizon. So you see 3 red lines diagonally across that limit to this event horizon. And that event horizon is famously known as the region of the spacetime. It's a null hypersurface that bounds the region, that separates the regions of spacetime from which observers can reach null infinity. So that's the right diamond. And the region from which observers cannot reach null infinity anymore. That's the black hole region. That's the upper triangle, say. And you see that if you start in the upper triangle, then invariably an observer will fall into the singularity at r equals 0, where the metric actually has a curvature and even a stronger type of singularity. So that's the event horizon. Associated with the event horizon is as a physical effect, the so-called redshift effect. That's now also indicated here with these 3 red lines. So these 3 red lines are meant to be signals sent out by an observer that falls into the black hole, so crosses the event horizon at the starting point of these lines. And then you have a dashed line on the right-hand side, which is another observer that stays outside the black hole and receives these signals. And so you see that the signals are sent roughly every second, let's say, but the observer on the right-hand side, the dashed observer, receives them in larger and larger time intervals. So in other words, signals get redshifted, and in fact, infinitely redshifted when the infalling observer crosses the event horizon. So that will play the role of a stabilizing mechanism when we study wave equations on these spacetimes. Another feature is, so I'm going to reuse this dashed line here, is the presence of trapping, which means null geodesics, paths of photons, let's say, that orbit the black hole indefinitely without ever falling into the black hole and without ever escaping towards null infinity. That is an obstacle towards wave decay, because you can imagine that wave packets remain localized, orbiting these black holes at a particular distance forever. There are also analogous solutions in the case that lambda is not equal to 0. They're then correspondingly called Schwarzschild de Sitter and Schwarzschild anti-de Sitter. And the Penrose diagrams explaining their causal structure are just obtained by taking the black hole part of Schwarzschild and the large scale part of de Sitter or anti-de Sitter space. So I will just briefly mention this here. So in the top picture, you see Schwarzschild de Sitter space. The event horizon is now marked as H+. And you have the central singularity at r equals 0, but there's now also the far end, which is like the Sitter space, the conformal boundary being r equals infinity, and there's an additional horizon, the cosmological horizon. So that horizon again has the same geometric or physical meaning. If you're on the upper right side of this horizon, then you cannot cross back into the shaded region that's sort of the vicinity of the black hole. The difference, however, is that if you're on the right-hand side of this cosmological horizon, then you do not encounter a singularity, but rather time-like geodesics are complete in that region. The Schwarzschild anti-de Sitter space is similar now in that you have again the black hole interior like in Schwarzschild, but now you see again the conformal time-like boundary. So if you study wave equations there, you again have to impose boundary conditions. The Schwarzschild family sits inside the larger family of Kerr black holes, which was discovered by Kerr in 1963. It's again an explicit solution of the Einstein vacuum equations, but the expression is somewhat lengthy. It was generalized to the case of general lambda by Carter in '68. And the Penrose diagram of a Kerr black hole, so for lambda equals 0, looks somewhat similar to the Schwarzschild case. So again, you have null infinity, as in the Minkowski or Schwarzschild case, but the black hole interior is what's different. So rather than having a central singularity at r equals 0, you see that the Penrose diagram continues further. And in fact, the metric is analytic up to and can be analytically extended across this Cauchy horizon. Okay, but from the perspective of the initial value problem, if you start with the Kerr initial data on sigma, the maximal development of these data where the solution of the Einstein equations is unique is really just this diamond. And once you cross the Cauchy horizon, where, as I said, the space-time metric is perfectly regular, there actually exist non-isometric extensions beyond. Okay, so the Kerr de Sitter case is again obtained, the Penrose diagram, by grafting the interior of Kerr with the exterior of Schwarzschild de Sitter, let's say. Likewise in the Kerr anti-de Sitter case, where again you have the time-like conformal boundary. Okay. Now, just as in the case of the maximally symmetric solutions, you can consider perturbations of these exact solutions by perturbing the initial data slightly. And so that leads to two types of problems, namely stability problems in the exterior of the black hole and stability or instability problems in the interior, which we will discuss in the sequel of the talk. Now, first of all, however, since the Einstein equations are this complicated nonlinear coupled system of quasi-linear hyperbolic or transport equations, depending on the formulation, it's very convenient to study simpler problems first. So the first simplification you can make is to study linear stability, which means that you throw away all the nonlinear terms in the Einstein equation, get a linear equation that you try to study and prove decay for its solutions. The next simplification is that you get rid, in addition, of the tensorial character of this equation. So rather than solving for a symmetric 2 tensor, you just try to solve for a complex valued scalar field, or real valued if you want. So that the problem of proving decay for solutions of the scalar wave equation on such a black hole spacetime, that's what we'll call toy stability. And there's a further simplification that applies to any sort of linear equation with the time translation symmetry. You can study the problem of mode stability, which is just the question whether or not there exists. So mode stability is the statement that there do not exist solutions of these of this linear equation that have this very particular time dependence, like a harmonic oscillator with complex frequency, omega. Okay, so corresponding to the two kinds of regions in these black hole spacetimes, we have two heuristic principles that we'll try to explain a bit. So heuristic principle number one, if you want to understand the stability of the exterior region of a black hole spacetime, the key analytically is to prove strong decay estimates for solutions of linear equations. And then you can upgrade this with some technical effort and an iteration scheme to a nonlinear small data result. So that's the blue region, that's the exterior region. In the interior region, there is an additional effect that I would just quickly like to point out, at the Cauchy horizon, which is the so-called blue shift effect that has a destabilizing effect, unlike the redshift effect. Namely, you have these 3 red lines on the top right, and these are signals emitted by some observer staying outside the black hole, sent into the black hole. And you have another thick black dashed line of an observer that crosses into the black hole, crosses the event horizon, and will cross the Cauchy horizon, receiving these signals. But now you see that the signals from the outside are sent with more and more time delay. However, the fat observer in the interior receives them at constant time intervals. So in other words, signals are blue shifted, so towards higher frequencies, which indicates that if sufficient energy falls in from the exterior of the black hole into the interior, then there's going to be an amplification happening that might lead to singularity formation. Okay, so that's the heuristic principle 2. Singular behavior in the interior you get from lower bounds for wave decay in the exterior. And regular behavior at the Cauchy horizon you get from decay, strong decay in the exterior. Okay, so let's look at some of the results in this direction in the increasing order of difficulty. So starting with the toy problem, we have the following result on decay of solutions of the scalar wave equation in the exterior of these various black hole spacetimes. So we look at box, the wave operator applied to psi is equal to 0, where G is one of those Kerr, de Sitter, anti-de Sitter, or just Kerr metrics with suitably regular and decaying initial conditions and possibly boundary conditions in the ADS case. Then you have the following results. When lambda is positive in the de Sitter case, and the black hole is very slowly rotating, or if the black hole rotation speed is not much restricted, but the cosmological constant is very small, as it is conjectured to be in our actual universe, then the solution of this scalar wave equation decays exponentially in time to a constant. And so the energy of that wave just decays exponentially. This was proved in the Schwarzschild de Sitter case by Boni Hafner, Melrose Sabarejo Bashi, and Maru Giannis, and the KDS per de Sitter case by Dyatlov Bashi and myself. In the case that the cosmological constant is equal to 0 and the black hole parameters are sub-extremal, the black hole is not rotating beyond a certain physical limit, the solution of the wave equation only decays inverse polynomially in time to 0, which was proved in 2016 by Defermas, Rodnyansky, and Stappentoff-Rothman. In the lambda negative case, the decay is even worse, namely you only have inverse logarithmic decay as proved by Gustav Holzegel and Smule VC under an assumption of the parameters satisfying against some physical bound. There is an interesting case of extremal black holes, Kerr black holes that rotate at exactly the maximal allowed speed, which was in particular studied by Aretakis, who discovered an instability saying that derivatives of the solution of the wave equation in that case do not actually exhibit any decay, and higher derivatives even blow up in time. And in the extremal case, non-axisymmetric solutions are not really understood at all. Turning to lower bounds, which is important, as I said, for the interior problem in particular, we have the following results. So again, for lambda positive solutions of the scalar wave equation don't just decay to 0, but you actually have to constants, but you actually have an asymptotic expansion into these modes, e to the minus I omega jt, times some spatial profiles a of x, up to exponentially decaying error terms. And so these frequencies omega j in this expansion here only depend on the black hole parameters. They're called resonances or quasi-normal modes in physics literature. In the case lambda equals 0, you do not have an expansion to exponentials, but what has been proved is, to leading order at least, the existence of a exactly inverse cubic decay. So you have a constant Q0 divided by T cubed plus more decaying error terms. That's the asymptotic behavior of scalar waves in the sub-extremal Kerr case. In the extremal, in the case of extremal black holes, at least in spherical symmetry for charged black holes, they're analogous but more subtle asymptotics also proved by Angelopoulos, Aretakis, and Gajic. Going back to the theorem, in the case lambda is negative, it was shown that this logarithmic decay is actually sharp. And indeed, Gustav and Smule VC, as well as Orangano, constructed quasi-modes or quasi-normal modes for the wave equation in that case that exhibit essentially this logarithmic decay also as a lower bound. If the parameters of these black holes violate a certain physical so-called Hawking real bound, then Dold actually constructed exponentially growing solutions. There are also analogous results as sharp asymptotics proved by Ma and Zhang for the Tucholsky equation, which is a particular scalar wave type equation that governs one component of the linearized Weil tensor in the linearized Einstein theory. Okay, some ideas and techniques used in the proof. There are mainly two approaches that are very interrelated. The first approach uses the time-honored energy method, the classical vector field method. And the idea is that you use vector field multipliers to prove energy boundedness or estimates, or show that certain energies of the wave are integrable in time, for instance. And in order to do that, you need to choose these vector field multipliers very carefully, in particular in the presence of these complicating geometric features like trapping and redshift. So at the event horizon, the corresponding multipliers were devised by Fermat and Rodniansky. At the trapped set, one has to do something somewhat more delicate. In the presence of an asymptotically flat end, like Minkowski space, Schwarzschild Kerr, there is also the RP method by Fermat and Rodniansky, which allows one to convert roughly space decay into time decay to get sort of stronger decay estimates. Okay, so in the case lambda positive, this trapping is unstable, it's so-called normally hyperbolic, and you have these two horizons through which waves can escape and never come back into the exterior region. That results in exponential decay. In the case lambda equals 0, you do have the asymptotically flat end, which always remains visible no matter how far waves have gotten. They can always scatter back and arrive back at an observer that stays in some, say, compact region. So you only have polynomial decay in that case, and when lambda is negative, I already discussed the logarithmic decay, and it is proved. So the proof of logarithmic decay is via energy methods, but the proof of the lower bound uses the aforementioned quasi-mode constructions. Another method uses directly the Fourier transform. Given that the wave equation under study is time translation invariant, you can just pass directly to the Fourier transform in time, formally replacing time derivatives by multiplication by a spectral parameter omega. And then you have to study the detailed properties of the resulting spectral family. So this box hat of omega is now a family depending analytically on omega of second order differential operators in the spatial variables. And so this is then studied typically using phase space analysis, which takes advantage of these particular features, normally hyperbolic trapping, the redshift effect, by applying a suitable black box result from microlocal analysis. So for instance, the trapping estimates by Wunsch-Dworsky-Dyatlov, or radial point estimates, as they're called, by Meros and Bashi. The results in that case, the decay and asymptotic results arise then as follows. In the case lambda is positive, one can show that this inverse of the spectral family is meromorphic. It's somewhat akin to the spectral family of asymptotically hyperbolic spaces. And the poles of this meromorphic family of operators are exactly these resonances. In the case lambda equals 0, you have a spectral family on an asymptotically flat space. And correspondingly, you have lower energy difficulties, and indeed the resolvent is not meromorphic anymore, but you have a logarithmic singularity at the origin, which was essentially discovered by Tataru, and that made more precise by Bashi and myself. In the case lambda negative, I already discussed the construction of quasi-modes and quasi-normal modes. In both approaches, a key ingredient is the aforementioned mode stability, so the absence of these purely oscillatory or exponentially growing solutions to the equation, which was originally proved by Whiting with some follow-up work. Okay, jumping directly over linear stability and coming to a nonlinear stability theorem for black holes, Bashi and I proved the following nonlinear stability result for slowly rotating Kerr-de Sitter black holes. The reason, in some sense, why this result was doable was that in the case lambda positive, you have exponential decay of perturbations. So if you have a nonlinear equation, that bodes well. And so what we prove is that in the context of the initial value problem, initial data that are very close to the initial data of a slowly rotating Kerr-de Sitter black hole evolve into a space-time containing a patch like this omega depicted here, which really contains a full neighborhood of the black hole exterior. So it contains the event horizon and contains the cosmological horizon, in which the metric G evolving from these initial data is equal to a Kerr-de Sitter metric plus an exponentially decaying sort of gravitational wave remainder term. This theorem is still, so this is only done in the slowly rotating case. So larger A is still an open problem. Even mode stability, in fact, is in general open. But other related results have been proved, for instance, for the Einstein-Maxwell equations for the so-called Kerr-Newman-de Sitter black holes. Just a brief word about the proof, not the one that Fang is currently developing based on Bootstrap, but the original one. So the idea is that we use a generalized harmonic gauge. So it's also depicted in the displayed equation down here. In order to turn the Einstein-Vacuum equation into a tensorial quasi-linear wave equation, one has to find what the final black hole parameters M and A are. And so one just regards them as unknowns in some iteration scheme, nonlinear iteration scheme, and also the exponentially decaying remainder will be treated as an unknown. We solve the nonlinear equation via an iteration, which in this case is the Nash-Moser or Newton iteration, if you want, in which one globally inverts, so globally in time, a linear equation at each step of this iteration. One important conceptual caveat is that the linear equations that arise in this way do not actually satisfy mode stability. But one can ensure by phrasing the Einstein equation coupled with the gauge condition suitably, one can arrange that all these exponentially growing modes of the linear equations are actually related to this coordinate freedom, to this diffeomorphism invariance. And the trick to getting rid of them is to also make the gauge condition flexible. And so regarding the gauge condition, which I encode here by this one form theta, to make it also part of the unknown. So in other words, if you choose theta carefully, you can suppress the emergence of these exponentially growing poor choices of coordinates. And then overall, roughly speaking, you solve this the system at the bottom here for the black hole parameters and the gauge condition, and of course for the metric. And the solvability and regularity theory involved here is based on uniform and time microlocal analysis of these perturbed spacetimes. And there was a sequence of works of Bashi and myself. Now, Gustav is going to take over to explain the case lambda equals 0.
Right. So recall from the toy problem, from the linear theory, that their perturbations only decay inverse polynomially, which makes the nonlinear problem much harder than compared with the exponential decay. And let's approach the problem by looking at Schwarzschild first. So recall that Schwarzschild, as Peter explained, sits as a one-parameter family inside the larger Kerr family. So nonlinear stability of Schwarzschild cannot hold unconditionally, and the best you can do is the following theorem, which we proved with Dafermos, Rodniansky, and Taylor. Nonlinear asymptotic stability holds for Schwarzschild black holes, provided the initial data lie on a codimension 3 submanifold of the moduli space of initial data. So because of this Kerr family, this codimension 3 assumption is in fact necessary, and the theorem is sharp. So all data that actually converge to Schwarzschild are covered by the theorem. I should also say that the codimension 3 submanifold, you can't say a priori what it is in the space of initial data, but it's constructed teleologically in the proof. Now, key to the proof is the linear theory, which was developed in an earlier paper with Dafermos and Rodniansky. And in particular, as we see on the next slide, the driving force is really having decay for these Tucholsky equations, and this decay estimates for the Tucholsky equations have been generalized also to the slowly rotating Kerr case. And in fact, we now know full linear stability statements for that range, for the very slowly rotating range, due to Anderson and collaborators, and also Peter and collaborators. We, in fact, know nonlinear stability for Kerr black holes with in the very slowly rotating case. Some very recent papers by Kleinemann, Scheftel, Georgi, Shen, and Kleinemann and Scheftel, which built on this Tucholsky linear theory, and also earlier work in the axisymmetric polarized setting by Kleinemann and Scheftel. I should also say that the general case of Kerr in the sub-extremal case with A smaller than M is completely open, but that there has been some progress in the linear theory, namely for the Tucholsky equation, proving decay estimates for Tucholsky in that range by Schlappendorf-Rothman and Teixeira da Costa. A few words about the proof of this theorem. As I said, the driving force is really the linearized theory in a double null gauge developed earlier. So there it is the case that two of the linearized null curvature components, these Tucholsky quantities, satisfy three important properties. First of all, they're gauge invariant, meaning that if you slightly change your double null foliation, let's say to order epsilon, then these quantities only see the change to order epsilon squared. So in linear theory, they don't see these infinitesimal diffeomorphisms. Second, these quantities satisfy a decoupled wave equation. So normally in double null gauge, you have this huge coupled system of equations, but these quantities, you can derive a decoupled wave equation for them. And what is more, you can actually, if you develop a suitable transformation theory, handle them with the techniques developed for the toy problem that Peter was describing earlier. And the third important property of these quantities is that they govern the dynamics in the following sense, that if they vanished globally, then you would know that the solution to your linearized system is pure gauge, meaning an infinitesimal diffeomorphism changing your double null gauge, plus a 3-parameter family of linearized Kerr solution, which described going to the nearby Kerr solutions. And the second important aspect of the linear theory is that solutions to the linearized system actually don't decay to 0. They don't even decay to this 3-parameter Kerr family of linearized Kerr solutions, but they decay to a pure gauge solution, to an infinitesimal diffeomorphism, which corresponds to the fact that if you want to see decay to 0, you have to normalize your double null foliation from the future in order to see decay. So once this is understood, then going from the linear to the nonlinear theory is done in a large bootstrap arguments based on the estimates that you proved in the linear theory. You have to construct these future normalized double null gauges. And what I advertised at the beginning of the talk, the double null gauge makes the null condition manifest. So handling the nonlinear errors, you can use techniques that have been understood 20 or 30 years ago for nonlinear wave equations. And the third aspect I want to say about the proof is the modulation of the angular momentum. So you decompose your space of initial data into disjoint 3-parameter families, and the statement is that for each 3-parameter family, you can find one member such that the corresponding initial data set converges to Schwarzschild. Okay, so that's the case lambda equals 0. Now let's look briefly at the case lambda smaller than 0. So recall that there even the maximally symmetric case was open, and I stated this conjecture that stability depends on the boundary conditions. Well, you expect something similar in the black hole case. In particular, if you impose a reflective boundary condition, you expect that Kerr ADS is unstable. So if you compare with a maximally symmetric case, note that here you have at least a little bit of decay, this slow inverse logarithmic decay in time, which of course makes the problem again harder. So it would be good to find a suitable model problem first, but there's one additional difficulty, and that is that the instability mechanism is actually manifestly non-spherically symmetric, because this slow decay comes from the very high angular modes, and so you can't study really the instability in the spherically symmetric case. So this is an interesting problem that should be addressed in the future. Okay, so now let's take a quick glance at the black hole interior. So we move now from the exterior into the black hole, and let's recall two things about this. First, the Penrose diagram of Kerr that Peter showed, which had this Cauchy horizon as a null boundary in the interior of the black hole. And let's also recall the heuristic principle that the singular behavior in the black hole should be governed by how much decay or how little decay you can establish on the exterior. And the first theorem that I want to present you to Dafermus and Luke is a stability statement that says that if you assume that on the exterior you decay to a Kerr solution according to the what you expect in the nonlinear stability problem to hold, then the Cauchy horizon is stable. So the maximum development will again have this Cauchy horizon, and the metric there will actually extend continuously. So this means that the Kerr interior is actually the generic behavior, and the Schwarzschild singularity type that we saw is non-generic, although there's some results that you can show that it's stable in polarized axisymmetry by Alexakis and Vounadavlos. And previous results on this theorem conclude or include things done for the linear scalar wave equation. Now, that's good. That's a stability statement. But according to the strong cosmic censorship, you would like the maximum development to be generically inextendable. So you would hope that if you ask for more regularity, then you can't extend. And that's still open in general. But fundamental progress was made for a spherically symmetric toy problem by Luke and O, who considered the Einstein-Maxwell scalar field system and proved that you cannot extend as a Lipschitz regular Lorentzian metric. So they actually showed C2, and this was later improved by Spiersky. And again, the key ingredient in the proof, as Peter described in the heuristic principle, is suitable lower bounds on the scalar field on the horizon. So for the scalar wave equation, so again, for linear problems, that these things have been established. Blow up of the energy, the H1 energy by Luke and Spiersky, assuming suitable bounds on the horizon, which were later proved by Peter and also by Angelopoulos and collaborators. And there's also recent work on the Tucholsky equation, which suggests that one should also be able to access the nonlinear problem in the future. And with this, I hand over back to Peter.
Thank you. So I am the person for non-zero lambda. And so in the case lambda positive, the stronger exponential decay of waves in the exterior leads to a stronger regularity, at least expectation, in the interior. And so there are results by Vashi and myself in the scalar wave equation, the toy model setting, where indeed you see the regularity scales exactly with the exponential decay rate in the exterior up to some geometric constant. And there are also, again, nonlinear results for a spherically symmetric toy model by Costa and collaborators. More interesting case is the case when lambda is negative in the anti-de Sitter setting. And so this was treated in a variety of works by Gustav Kehle. So he showed in the spherically symmetric Reis-Nordström anti-de Sitter setting that linear waves are indeed still continuous up to the Cauchy horizon, but their energy blows up. On Kerr anti-de Sitter spacetimes, it's a rather dramatic novel phenomenon, namely for black hole parameters A and M that satisfy a certain Diophantine condition arising from some resonance condition between the quasimodes in the exterior and the poles of a scattering operator in the interior. He shows that under this bare generic and Lebesgue exceptional condition, solutions of the wave equation typically blow up in amplitude in the interior. And conjecturally, if this condition is violated, then actually a solution of the wave equation remain bounded. So there's somehow almost number theory entering into this question of blow up or not. So in the remaining little time, I just want to mention a few other developments. So large data regimes is one very interesting arena. Large data meaning you're far from any of the explicit solutions. And given the nonlinear character of the Einstein equations, that's very hard to analyze in general. So there are two standard means to get to that setting. One is to impose special symmetries, or such as spherical symmetry or approximate self-similarity or such. And the other approach is via a very careful sort of deep choice of an ansatz in which some nonlinear terms of the Einstein equation pair favorably. So perhaps some term is large in some direction where the metric oscillates wildly, but they're paired in the nonlinearity with the components of the metric, say, where the metric is very regular or doesn't oscillate. And so just as a sample here, there's a theorem by Rodniansky and Stapenthal-Rothman that establishes, for instance, the existence of a large class of large data, so far from explicit solutions. Solutions of the Einstein vacuum equation that contain naked singularities. So that means singularities that are visible to any arbitrarily far away observer. And previous work on naked singularities and their stability and instability properties was done in spherical symmetry for a toy model, therefore, by Christodoulou in the 90s. Other large data regimes include the trapped surface formation and foundational work by Christodoulou on the focusing of gravitational waves via so-called short pulse method, or the Luke-Rodniansky theory of impulsive gravitational waves, where the Riemann curvature tensor has a singularity that scales like a delta distribution. Just very briefly, some other settings of key interest are, but that have not been studied much, are spacetimes containing several black holes. That's of course of astrophysical interest. For instance, it would be extremely nice to construct spacetimes containing several black holes, or they contain black hole mergers. But that's, again, one of those large data regimes where one has to find an appropriate ansatz, very simply put. Other developments include inverse problems for Lorentzian metrics, where you try to recover a Lorentzian metric, perhaps up to a conformal factor, from faraway measurements of, say, the light cones from stellar explosions in this faraway set, or from source to solution maps for nonlinear wave equations. There are many other topics that we cannot cover in this lecture, such as matter models, in particular Einstein-Vlasov, which is of importance in galactic astrophysics, or weak limits of high-frequency solutions of the Einstein equations and the so-called Burnett's conjecture, and very interestingly, of course, connection to experiments like black hole mergers, as already mentioned, for the ring down phenomenon. And so we apologize for all those researchers in these fields that we did not have the time and space to talk about these topics. And with that, I would like to thank you for your attention on behalf of Gustav as well. Thank you very much.
Thank you.